Hello, this is Miss Moore, and we are now going to finish our discussion on heat flow and enthalpy. Today's essential question: how does heat move through endothermic and exothermic reactions? All right, enthalpy. The heat absorbed or released in a reaction depends on the difference in a quantity called enthalpy. The enthalpy of a substance is basically its energy, but it's the energy under a particular set of conditions. And like energy, enthalpy of a substance depends on its temperature, its physical state, and its composition, or what it's made up of. The changes in enthalpy is represented by a triangle known as delta H. That triangle, in any circumstance, means change in. Okay, so change in enthalpy, delta H, change in enthalpy. So delta, the triangle is delta. In science, triangle delta is used to represent change or difference. All right, so delta H, something you need to know. The change in enthalpy equals the change in enthalpy of the products minus the change in enthalpy of the reactants, or delta H equals delta H products minus delta H reactants. The delta H of an endothermic reaction will be a positive number, right, because it's absorbing energy. And another way to think about it is that the products, we talked about this in the last lecture, the energy of the product molecules is greater in an endothermic reaction than the energy of the reactant molecules, okay? The delta H of an exothermic reaction will be a negative number because you're releasing energy. Okay, thermochemical equations. Thermochemical equation is a chemical equation that includes enthalpy or heat energy. So here's our normal balanced equation, and here is our heat written as 802.2 kilojoules. This is an exothermic reaction. We can also, if you guys remember like mole-mole ratio, we can come up with an equality using the number of moles of any of these atoms and the amount of energy. So for example, this first one here, if we were to compare CH4 and the energy or enthalpy, we would have an equality of 1 mole CH4 equals 802.2 kilojoules, meaning for every 1 mole of CH4 used, we will create 802.2 kilojoules. If we were instead to talk about water, for every 2 mole of water produced, you also produce 802.2 kilojoules. Okay, so this is a new equality. So to predict the amount of energy produced, you can use energy and one of the coefficients from the balanced equation as the equality or conversion factor, and then use the factor label method. Okay, so let's try a quick thermochemical equations practice problem, and this is basically like doing stoichiometry, same thing. So if we have 32 grams of O2, how much heat will be produced? Okay, so the first thing you're going to have to do, because we want to get to moles, right? This is moles. So you're going to do grams of O2 to moles of O2. So we're going to have 32.3 grams of O2 over 1. And we'll be using the equality 1 mole O2 equals the molar mass of O2, which is 16.00 plus 16.00, or 32.00 grams of O2. And we'll put that in the grid, 32.00 grams O2 on the bottom, 1 mole O2 on the top. Grams and grams cancel out. So now that we've got to mole O2, we can use the, like the mole-mole ratio, but this time we'll call it the mole energy ratio from the balanced equation to figure out the amount of energy produced. So we have moles of O2 to that much energy. Now, what does it mean? This here says negative 802 kilojoules. Why does it say negative 802.2 kilojoules? Well, because it's an exothermic reaction, which means that the energy goes on the product side. Okay, so now that's going to be our equality. 2 mole O2 equals 802.2 kilojoules. So who's going to go on the bottom? Well, 2 mole O2, and on the top we'll go 802.2 kilojoules. Okay, and those cross out. Now all we have to do is multiply and divide. Okay, so when I multiply it across the top, I got a big old number here, 25911.06 kilojoules. And when multiplying across the bottom, I came up with 64. From there we divide, giving us 404.86 and so forth kilojoules. That doesn't fit. Kilojoules. Okay, now if we go back and look at sig figs, we have 3 sig figs, and here we have 4, so we're going to have 3 sig figs, so our final answer is going to be 405 kilojoules. So if you start with 32.3 grams of oxygen, you will be creating 405 kilojoules of energy. And that's all there is to it. Have a good one.